deal with making a pinion for this little trapeze movement. Let's remove these dial works pieces here, take off the clip, and we come down and let's look at this wheel and its pinion. This pinion has 10 teeth, and it is driven from the center shaft pinion to the wheel, from this pinion then to the hour hand via this wheel. Now, what we will deal in this particular tape is the replacement of this pinion right here. Now, this pinion is staked into the wheel. It has a through bore on it that journals on a stud here on the front plate. Well, let's set the movement aside and take a look at removing the pinion from the wheel. To remove the pinion from the wheel, we need to find a bench block hole that fits the pinion diameter rather closely, and a punch that will overshoot this section of the pinion, and then we'll drive the pinion free from the wheel. Let's see what we have here with the punches. Let's try this one at this point. You can press that. And as we sink that ever so slightly, let's see what we have. I don't believe we dislodged the pinion in that operation. Let's find another punch and continue there. Let's try a flat face punch on the end here. It's not to damage this pipe. And one more tap, and we did have it essentially dislodged. Now this wheel, when we drove the pinion out, has taken on a slight dish, just an ever so slight dish. We would like to sit that back in order by on a hard, smooth surface bench block, and get our wheel back perfectly flat again. Let's lift the pinion, take a look at that. Now to handle this pinion, let's slip it on a punch so that we can look at it. We have to duplicate this, and it has a diameter. When we look at the diameter of it, it's 325 thousandths of an inch in diameter. It has 10 teeth. Its length is 135 thousandths of an inch long. That is the pinion section of it. And it has a shoulder that permits riveting into the wheel, and then a continuation of a small pipe down here. Now what we will do, we will make up a blank piece of blank stock to cut the pinion from. Now it's not readily feasible to hold this in a wheel cutting engine blank that looks like that. So what we will do is to make up a blank with a handle on it. That handle will reach down something like about this length, run on out in this direction, and we will use one end of that handle to support the stock in the wheel cutting engine. We will use the other end as a center support to make this rigid to make the cut. And when the pinion is, the leaves are cut in place, then we will trim off the handles and rework the piece to become the finished pinion. All right, let's pause here, and then we'll look at another step of the operation. The piece of raw material that I've selected here is a piece of 3/8 inch rod stock. This is brass, and it's about 1 5/8 long. It's pretty rough on the end. This is something that just come from the scrap. One of the things that you can always remember that all of this raw material is new on the inside, even though it may look pretty rough on the outside. We've set this piece of stock in a 3-jaw chuck. We'll take this to the lathe. We'll locate a true center out here. We'll support that true center on a center in the tailstock, and then we will begin to machine this material down to make the blank that we will ultimately cut our pinion from. This is the pinion we'll be duplicating. This pinion is not a bad pinion. It's that we're going through the process of making a new pinion. All right, let's pause again, and we'll go to the lathe and set this up and begin the machining operation. Working here, this is a dual pedestal lathe, pedestal here. The bed is about 15 inches long. This is headstock height is 50 millimeters. Webster Whitcomb spindle, and the spindle takes all of the Webster Whitcomb attachments that we know in the American watchmaker's lathe. However, the bed is a V-bed lathe and must have a special shoe or adaptation to the bed if we use American watchmaker's lathe parts. The slide rest that we'll be using is American made. This is made by the Levin Company. It's a 3-deck slide rest, and tool holder holds 3/16-inch square bits. This slide rest is adapted to take dial gauges or micrometer stops on both the horizontal and the longitudinal feet. The thing that we will do first is use a tip-over tool rest and the watchmaker's lathe graver. We'll catch a center here to drill a hole to. We want to first drill a center hole in the tailstock. So let's catch that center and see what we can do with this. We'll start the lathe running. Put on a little high intensity light here, and go in here with the handheld graver and locate a center. The lathe is running quite slowly, and we have that. Let's take this off, put on a drilling tailstock, and we will drill this. I believe I'll use a 1/16-inch drill bit. We'll drill into this tailstock, into this stock from the tailstock, and we'll later enlarge that hole as the pivot hole of the pinion that we ultimately complete. So let's pause, and I'll gather some tools, and then we'll begin that operation. Returning to the camera, we have set up here the tailstock, the lever feed, a Jacob-style drill chuck, and a 1/16-inch bit. We will sink a hole in this center that we caught with the handheld graver. Let's turn on here. We'll pick the motor speed up some. Back the chuck out. Lock up the tailstock, and we begin to drill. It's beginning to sink into the stock. I'm approaching 1/4 inch deep right now. Approaching 1/4 inch deep. That is completely adequate to support the center that we will be using. Let's take the drill out of the tailstock. Take the Jacob's chuck out. and we'll slip the bit out of the chuck to protect the bit, and we'll look here for a center. Place this center in the tailstock, snug that up good, snug this up. Now we can pull up, touch down in here, and lock up the tailstock. We'll put a drop of oil in, on up into the hole, and now we will be able to make the heavier machine cuts that we need to make right here in forming our pinion blank. Let's pause and I'll gather some more tools, and we'll gather the dimensions that we want to work to. We'll begin there in a few moments. While we were off the camera, I changed the tailstock runner. The particular center that I had in the tailstock was a bit too short to allow me working space for my tool slide here, so we've changed to a different runner that has longer overhang length. We faced the end, the very end of the stock that we have, and I took a cut here to see if we were going to be able to true up to the ultimate diameter that we want, and indeed we can. And what I'll do, I'll continue this cut and work this down to 50 millimeters in diameter, which is a size that we can readily hold in a collet in the wheel cutting engine. And this will be the tang that we will ultimately hold the material by in the wheel cutting engine. So we'll go for 50 millimeters in diameter there, and the length that we have here is in rough numbers 5/8 of an inch long. So let's turn back on and work on that cut. We'll add a little oil to the center and pull the tailstock up and begin the cut. A little rough right on the end there. That will clear up after a pass or so. We're coming back. The cut is now turning very smooth. This brass is quite free machining. We're looking for 50 millimeters in diameter. 50 millimeters, and just in round numbers, is 2/10 of an inch. I have a caliper here that measures in the English system, so we'll take a look here after this pass and see how much that we have to go. We have a considerable distance to go yet. The measurement that we have here is 310 thousandths, and we'll be going for 5 millimeters, which is about 199 thousandths. Another cut, and we're back out. This particular lathe is built by Ideal Manufacturing and Engineering Company of London. I had this custom built there in London about the early 1960s, 1961 or 62, somewhere in that particular period. Back out and take another look at the dimension that we're on. We're down to 268 thousandths of an inch now. We're going to about 200. This lathe is powered with a 1/10 horsepower direct current motor. The control that goes along with the lathe converts the alternating current to direct current, senses the speed, and controls the speed to a preset value. It's a very fine speed control system. The lathe is very handsomely powered, and the control is made by General Radio Corporation of the United States, and the motor was built by the Bodine Electric Company, also of the United States. Now, as I reduce this diameter more, I may have to change the angle of my tool bit because I'm approaching the taper. On this 60-degree center is in the tailstock. Also, to facilitate arriving at my cut more readily, I'm going to install a dial gauge on the horizontal slide. So we'll pause and get the dial gauge and get that in place. Returning to the job, we'll measure the diameter here, and at this reading I have 219 thousandths of an inch, and we're going for 5 millimeters. Now, 5 millimeters is in the order of 199 thousandths of an inch, about 2/10 of a rough number. We'll dial this gauge into 0, and I'll pull up for the next cut. Remember that we're measuring on the radius of the work with this gauge. So let's pull up 5 thousandths of an inch, which should take 10 off of the work, off of this stop, and see what we have here. Approaching the end of the cut, and let's measure that. And we're approaching what we're looking for. I want to turn this tool bit ever so slightly for clearance space against the center as we make the final cut here, and see what we have. This tool bit around just a bit, and back out to the beginning of the cut. And dial in a little more. See what we have now. Out, and we'll take another measurement. I believe we're okay right there. I need to chamfer the end of the stock out here just ever so slightly. I think I'll touch that with a handheld bit. Remove the dial gauge, get the slide off, and tip over tool rest. Lock that up, and let's see. Right there. Now with a handheld tool bit, I should have done this while I had the tool slide in, but I'll finish with a handheld bit. We'll square up this shoulder over here, clean it up, right at the edge of where we were cutting. If I can get my hand out of the photograph a little bit. See what we have now. We would expect this to fit a number 50 collet, and find a number 50 here in the block. That is snug tight, just what we're looking for, and that's what we will use for the handle in subsequent turning operations. Now, before we go further,
While I'm on this true axis here, I want to take just an ever so slight cut on this rough section. So let's make a pass there. Tool slide in place. We're up closer to the chuck, so we don't have to have the center at this point. Get in closer to the chuck with the tool slide. Be sure that we're not in danger of touching down on the chuck with one of the slides. And we'll take a pass around here. Touch the chuck. Touch the chuck. We want to back out and move our tool bit up. Move the tool bit over a piece. We have a true surface there. Pull off the tool slide, shut down the motor, unlock the work, that out, chuck off. All right, let's place this number 50. Wire collet in here, and I need a tailstock spacer for this, right there. And we'll set our work in this direction. Very, very snug in that collet. Let's see how we run. We're running very true in the machine section here. Of course, this section is rough. Now, what we will do, we'll go into this opposite end, and we will form a center so that we can support this on the tailstock and continue the machine work. Back with our hand-held tool. Locate center. Test the center for trueness with a scriber. You're okay. Shut down. Now let's drill drill this so that we can support the center. Now I have to change to the lever feed tailstock to do that, so we'll go off camera while I'm making change on the tools. Returning to the camera, we have exchanged the tailstock to the lever from the center runner to the lever feed, the Jacob style drill bit, and we're ready to drill. Let's drop a droplet of oil there, and we'll drill our hole. As in the other end, we'll sink this hole about 1/4 of an inch deep. And we're about there. So let's take this down. out the drill chuck, screw off the lever, and go back in with the dead center. And we can go right in to the dead center with this. Okay. Back again, we will return to the tool slide. Now the objective here is twofold. We want to set the major diameter of the pinion and the length that the pinion will be cut. And then we want to move out some distance here and prepare us a true handle to hold this by on this end. I think for simplicity I'll cut this end for 1/4 of an inch, and 1/4 of an inch can be held in a about 6.2 or 3 metric collet. So let's proceed with that. First we'll head for the 1/4 of an inch on the outboard end. Cutting a little faster than my lathe can pull right there. I was installing the headstock. The belts that are used on this lathe are very, very lightweight and very pliable. These belts are made from leather boot laces, about 1/8 of an inch square, well oil soap, and spliced with some little steel hooks. Those steel hooks is made from paper clips. This is the lathe that I do some of my most delicate work on. I want those belts to be very soft and pull very smoothly so that there's not even a trace of tremor in the machining operation in the most delicate work. Let's look at the diameter we're on at the moment. I'm on 315 thousandths. We're going for 250. This material machines very, very nicely. I'm at 300. We'll take a couple more cuts and then measure again. A little oil on the center. Let's see if we can look at the chips that's coming off of this. Chips that are being cut away are coming off in flakes. Though this is free machining, the tool bit is not ground to cut long thin spirals as we've seen in some other illustrations. This tool bit is ground as a chip breaker on the end, and it breaks the chips up so they don't get caught and wound around the spindle. I'm measuring 264 thousandths, and we're going for 250. So let's make a pass here. See what we have there. I am 257. Take off about 7 more thousandths. All right, let's try again. See what we have. And we're at 249. We overshot the distance by 1/1000th of an inch, which is inconsequential. Let's open up the center and trim this tail end just a little bit cleaner, because we'll be using that as a support in the wheel cutting engine. Got a little bit of tool chatter there. We're not supporting this as rigidly as we were when we had the tail center in it. And just break the edge here, just a tiny amount. Now let's get our pinion and size this area right here. Back up on the shank, we'll size that area to the major diameter of the pinion. We'll return in a few moments. Returning to the camera, we're ready to finish the blank to the major diameter of the pinion. I measured this again, and this is 320 thousandths of an inch. This is the pinion slipped on a punch to keep from dropping it here, and it is ever so slightly out of round. It ranges from about 320 to about 330 thousandths of an inch in diameter, depending on which of the leaves we measure across. So we've set this at about 325 thousandths of an inch, which is about the mean of the values that we have there. So let's make a cut and then look at our measurement. Let's see how we're doing with that particular cut. We're at 352. Let's go again. Measure again. 348. We'll do ourselves well to set this gauge up and use that to find our way. Off and measure again. You may notice I'm reaching down here for a switch on this lathe when the switch is really back here. The switch is not located at the same place on each of the lathes that I use, and I instinctively reach to the wrong place, I'll transfer the switch. I'm at 331. So let's inspect the dial gauge, and we'll pull up a judgment amount there and see if we can get that. In this cut. I have 326 right there. So let's leave that be. Now there's another problem that we have in sizing this blank. The riveting shoulder on this pinion is 220 thousandths of an inch in diameter, and when I look at that, I see the cutter on the previous pinion was going into that riveting shoulder. That says that I can't pull that cutter out over in this area. I can't pull that gear hob out into this area and rotate my blank, with that being 1/4 of an inch in diameter. If I hold it by this end and size to the other end, which is 200 thousandths of an inch in diameter, I don't believe I can either. I see the tang where this was originally made is 150 thousandths of an inch in diameter out here. So we're going to have to reduce one or the other of these ends for a place for the gear cutter to have a run out so that we can rotate the stock between cuts. I believe, being I have this true in the lathe, I will reduce this tang here to the 150 thousandths of an inch, and instead of holding in the 1/4 inch collet, or about the 0.61 or 62, or the 6.1 or 6.2 millimeter collet, I'll just use a smaller collet. So we better take this down right out here. Take this down to 150 thousandths of an inch on the original unit. I've run out of travel on my slide. I must move my tool slide over on the bed ever so slightly. The shoe is locked up very tight on the bed. There we are. And we will continue. Taking a very rapid cut here, and taking a reverse cut. See where we measure. I'm at 205. Going for about 150. At 200, let's begin to use the dial gauge. What kind of success we're having there. We're at 180. We got 5 on the forward cut. Take 5 more on the reverse cut. That should put us in the order of 155 or 160. Or 161. There's some oil on the center. Where are we now? 156. All right, we should be there. And we're okay. Let's deburr this slightly with a number 5 cut file. Break the edge and out of the collar. Got a skin tight fit in that collar. There we go. Out we come. All right, this is the blank that we will make the pinion from. Let's see if we can get this someplace that we can see what we have here. One tang is 2/10 of an inch in diameter, about number 50 collet. The other is 150 thousandths of an inch in diameter over here. We will hold this in the wheel cutting engine. We will support it by one end, which we will hold in the indexing attachment, and we will support the opposite end in a center. We will make progressive cuts through here. We're going to cut 10 teeth, and then we will have the pinion in rough form. So let me prepare the wheel cutting engine, and we'll be back a little later and go for that. Returning to the milling machine and the setup to make the pinion, being that there is a considerable amount of setup to be made, I went ahead with some of this off camera just to save time that would be redundant in the mind of the viewer. Here's the milling machine. This is the profiled gear cutter on the spindle. This is a horizontal spindle milling machine. This is the vertical slide control. It's just out of the picture. It's up this shank right here that sets the height of this cutter like this. In the foreground that is up this lever here is the feed lever, which would make the pass of the part through the cutter. This little machinist clamp is a stop on the carriage. This is screwed down on the carriage so that when we make the backstroke that we are not permitted to run the milling cutter into the hardened spindle of the indexing device. This is the indexing head. The indexing head has a plate here with about 10 or 12 rows of holes in it, numbering from about 50 to 90. and an index pin here. But in cutting this pinion, we will not use that because, for instance, if we were using 60 holes, cutting 10 teeth, we'd have to count 6 holes in index. That becomes a nuisance and less necessary. We have a second plate right here, an edge notch plate that is behind the main disc. And we have a latch at this point, a chisel latch that latches into a slot there. And that has 10 positions around, so we simply go to the next position after each cut. The blank that we made is held in a collet right here. This is the small end of the blank that's around 150 thousandths of an inch. This is the end that's 5 millimeters. This is caught in the collet, not very deep, but very tight. Here's the sector that we'll be cutting the pinion from, and this is a support center out on this end. This support center is very rigid here, and the cut is made with the cutter rotating in this direction, so the cutting force is into that center. That is the support to hold us up. We will cut 10 teeth. If you have looked at the Huckabee Random Clock Talk on some other tapes, you will understand how that the cutter is chosen. This cutter is made to cut 10 teeth. It's in 0.65 module, which is the module of the gear that we were in. One of the other tapes tells how that we derive those figures and what they mean. We size the OD of the cutter, not the cutter, of the blank, equal to the pinion that we're duplicating. We will sink this cutter in to a depth that when we make a pass, index one position, make a pass again, that we bring the teeth to a sharp knife edge crest. That is the reason for sizing the blank precisely, because we use the OD of the blank and the crest of the tooth to tell when the depthing is proper. Now let's start the motor. I'll have to reach over the top here to start the motor and see what we have. Make a pass. I've already made 2 passes through this. You can hear the cutter just skidding in place there. Go back against the stop. Turn the index, and we'll make another pass. This is the tooth. This is the 2 teeth that I had cut previously before we turned the camera on again. All right, we'll go to the next tooth. That cutter is touching down ever so slightly on this underneath shank here. That could have been sized about 10 thousandths of an inch smaller in diameter and obviated that. It was of no consequence in the end job or in what we're doing. We're now making the next cut. The cutter is going about 2,000 RPM. This brass is not extremely hard. Consequently, we don't have to lubricate it as we did some of the previous work that we were doing. Go to the next tooth. Do this again. And we will progress until we have made 10 passes, and then we will have the pinion in the rough. Next pass. Derbyshire micromill was built in the World War I era. It's powered by a 1/3 horsepower electric motor sitting over on the bench. It's driven back in the rear region, back in here, driven by a belt. It's a piece of rawhide harness lacing. It's a very soft, very pliable belt. That belt off so that it runs extremely smooth on the pulleys and with no vibration. like we have about 2 more passes to go after this one, possibly 3. I believe this is the last pass. And we'll make one more. That should set us in the first pass that we made, and I can hear the cutter just touching down in it. Let's cut power and take a look at what we have. Cutter stopped. We'll get down in close with the eye look and see how we look. The thing that I see in this, that we should have gone ever so slightly deeper. Just ever so slightly deeper. We can correct that right here. We'll make a pass through each tube again. We're going to pull down about 5/1000ths of an inch. We'll make 10 passes. There's the first. Second. Back into a previous cut. Let's shut off and take a look now. And that looks just real fine. We'll lift the cutter. Lift the cutter up. Let's find some of our tools here. Set the center off. Just like the drawbar. Pull out the pinion. Now, we have the pinion in the midst, in the central section of a stick. Now the pinion is too long here. It does not have the hub machined on it. It does not have the spacing tang under the bottom side. It does not have the hole drilled through the center. We will take those up in subsequent operations when we mount the wheel. So there we are, is the basic process of cutting the rough pinion. I'll turn off the camera here and clean up the bench area, gather up the tools that we need to finish the machining, and we will continue. We'll mount this onto the wheel, put it into the clock, and set it into operation. So this is the way that you would go with the making a brass pinion. If this were a pinion integral with an arbor and it was steel, you would do the same thing. The process would be identical. You would probably rough your arbor out, possibly cut the pivots on it first. And you would narrow this down considerably. This is about 3/8 of an inch long. If it were a trained pinion, the length of it would have been held considerably shorter. But you would machine the teeth, and then you would later add the hub and the wheel, etc. So this is the process of pinion making. I'm J.M. Huckabee, certified master clockmaker and fellow with the British Horological Institute. You're looking at the tools in the shop of Huckabee Shop on the J.B. Ranch just north of Austin, Texas. Returning to the lathe, we will begin to prepare the pinion to mount on the wheel. Here is the piece that we cut a few minutes ago. The tooth section is in the central region, and the two tangs, we will go back into the lathe, hold by the 50mm tang, which is, or 5mm tang, which is here, and start working on the end of the pinion. We set this in the number 50 chuck, ring it in place, tighten it up good and tight, and take a look at it. We're okay in the way we run. Let's cut this tang away right here. So the first thing we do with the saw, we saw off this handle. This is one of the handles. We have two handles on this. We'll cut that one away. This saw blade that I'm using is a very, very tiny blade. Really a bit too fine for this work, but for a single cut it will suffice all right. We should be approximately passing through here any moment. Let's see if that's about the point of drop-off, and yes it is. We'll set that aside. Let's go into the lathe with the tool slide, and prepare to make our cuts there. Get on the safety glasses, and we'll take a look. We'll run this pretty high speed. I have a very pointed tool, so that when I cut into the end of that pinion, that I don't smear the shape of the pinion teeth. I'll be machining right up against the riveting seat on that, and taking the cut, we're on the edge of the teeth at this point, and we have to cut back the riveting shoulder. I think at this point we will trial the measurement against the original pinion. I have it latched on the brooch to keep from losing it, and have a good little distance to go. Let me go off the camera and gather another tool. We'll be right back. Back on the camera, we're machining the wheel seat on this pinion, and we have just a little distance to go yet. We're approaching our final dimension. I made a few cuts on this while the camera was off. And let's try the wheel on the seat here now. We're approaching our final dimension. what we have. You have to increase that seat depth ever so slightly. Check that. Now let's check the pipe tang. And a little bit more there. All right, let's locate center with the handheld bit. And drill the hole. Let's see that we're centered perfectly. And we are. Now we'll set up our drill bit, and we'll drill the hole that's to pass through. We can turn off the camera. We'll locate the plate and see the diameter of the bit that we have to have, and locate that and be back and drill in just a moment. Returning to the machine work, we look on this plate, and the stud here is 99 thousandths of an inch in diameter, and I've chosen a drill bit that is 86. We will drill that, and then we will re-drill the second pass through. This material is drilling quite easy, much easier than I had expected. These drill bits are extremely sharp, and the drilling is just almost effortless in this. The drill is going in very straight. I feel no evidence of a tremor of the bit. I'm riding my finger on the bit to feel of it. It's going in very, very nicely. Let's inspect the depth. I believe I'm approaching a half-inch deep. About a half-inch deep there. So let's take the bit out and then go in with one of the finish diameter. The object in pre-drilling and re-drilling is all bits have a tendency to over-drill their diameter, and by using this technique you reduce the amount that the bit will over-drill. Let's find one here. Matter of fact, we have one in the index that's labeled 99 thousandths of an inch, which is the exact amount that the stud that this is to go over measures. Presuming this to over-drill ever so slightly, we should come out with a good fit doing this. bit acting simply as a final reamer to the hole. Let's back out and try the stud in the hole. That is, if we can get it up into position here. And it will not go in the hole. The stud will not go in that hole. Let me measure again. It will not go in the hole. Let's go to the next larger bit size and see what we have in the index. I have a 101, a 99 thousandths to a 101. The next bit is 2 thousandths of an inch larger. Leave out. Place just a little drop of oil on this. Get out the hole. Try the pin. And that fits very, very nicely. Very nicely. Let's look at the tang. We need to reduce the length of that about 5 thousandths of an inch and chamfer that hole. Chamfer the hole. Make the outside edge slightly. Check our riveting seat on the wheel. Looks good there. So let's pull the piece from the machine. Look a little more careful. Let's try this full depth. Beautiful. Very, very nice. Let's try another item here. Let me cut the camera and I'll look for another tool. Turning back to the camera, one of the inspections that we need to make before we mount this wheel up is to be sure that this pinion that we have has perfect mating teeth to its adjacent wheel. Here is the wheel that carries the hour hand pipe, sometimes called the hour wheel, and this would be, in the same general vernacular, would be the minute pinion. And we slip that minute pinion, this is the pinion still with a handle on it, we slip that over the stud and we spin this wheel. And we see that we are very free, this pinion spinning, so that we know that we have a perfectly sized pinion. And the remaining job that we have is to cut the handle off. We cut away the handle and we're ready to mount it up as the finished part. We'll lay the movement aside and we'll compare to see about how long that this should be when it's finished. And we'll just take the saw and saw it right off right here in the lathe. We've got a holding problem when we go to machine this remaining end. So it says that we want to cut it off so that we don't have any more machine work to do than is absolutely necessary. So we start here and we saw away the second handle. Need to tip that camera up just a little to see what we're doing. We have this in the lathe, and we're going to saw away the handle, and then we'll do a little more machine work and assemble it to the finished mechanism. This is a very fine blade. I'm attempting to cut with a fine blade because I'm sawing right through pinion teeth and whatnot. pinion, the machine part of the pinion is really longer than was necessary. And when we machine the end, we don't want to smear those pinion teeth in any way. Here is the pinion that we have almost finished. Here is the one that we're replacing. Let's pull the handle out and see what we can do to finish this off. I have to find a collet to hold this. That collet will have to be 210,000ths of an inch in diameter. I don't know if I have one in this block or not. It looks like we don't have a collet in this block. This is my rough collets. We don't have a collet in that block that would fit. Let me turn off the camera and I'll go to another group of collets and we'll pick one up and be right back. We have the suitable collet now. The one we needed was a number 57. That isn't a very commonly used collet. In another set of more precision collets that I own, I have every size from number 2 through number 70. So it's just a matter of going and looking into another group to find what we needed. Now let's get down here where we can face the end of that pinion. I want to run that speed up real high and take extremely small cuts. I don't want to pull this out of the collet. Taking the first cut. And another. And this tool bit has an extremely sharp point, and we don't want to smear the ends of those pinion teeth. And hear the tool bit touching down on the ends of the teeth. Hear the sing. Let's compare the length of the two. I believe that we're okay right where we are. We'll take the handheld tool, break the mouth of the hole. We can't do much with the ends of the teeth. We just have to cut those clean. The mouth of the hole. We'll take a little soft brass suede shoe brush. We'll brush the flash from those teeth. We don't want to drop this in the floor now when we start. Got too much work in it, so we slip it on a scriber. Lift it out. Let's try this. Let's trial fit this on the plate. Drop it on the stud, on the plate, look at the depth of meshing, and I have yet just a little bit of problem here. The clip might not go on. We need to shorten it just a little more. Back in here. And we'll do some more of the same thing. cut, taking the second cut. Recut that chamfer. And brush off again. Try that on the stud on the plate. Beautiful, beautiful. Don't know if we can see this in the camera. The pinion that we're speaking of is right here. Pointer, right there, and it rolls very, very nicely, and all that remains is to rivet the wheel in place. Okay, let's look at the wheel. Inspect the wheel. We'll leave top side, just as it was before, and it will look like that. Now what we have to do, this is light press fit in place. What we have to do is to take our staking set and rivet this shoulder right here in place. And when we do, we will be essentially finished. Let's turn the camera off and find our staking tools, and then we'll look at that operation. Let's talk about the riveting operation. I have a shoulder on the pinion that passes through the wheel right in this region. And that shoulder is about 60 thousandths of an inch wide. I can see the undercut in it where each pinion tooth also passed out, left a small groove there. And the thing I need to do is to upset that edge just enough to lock the pinion in place. It's adequately tight right now to drive the hands, but we don't want it to ever become dislodged. I think I'll do that with a flat face punch. This is a little Starrett flat face punch. I'll sit on the edge of that shoulder, hold it here, and just tap it about like that. We'll turn it a half turn and do the same thing again. And we'll turn a quarter turn and again, and on the other side. What we've done, we have locked that in place. 4 stakes on there. Let me look at it with the eye loop, be sure that we're okay. And all 4 of them look very good. Now this wheel should be essentially run essentially true in round and flat, because we're going on to machine surfaces, and I can't get that. These pins are touching each other, and I can't set that in place on that depthing tool. Let's get the movement and see how it looks on the movement. Well, we can't spin the piece on the movement, can't spin it in the depthing tool, but I have a punch here that I can spin this on. And we do like this, and the wheel is very good and flat, and it looks likewise good in round. So as this would assemble into the movement, it will go like this, and like this. And let me see that I have adequate space for the clip to go under this. And I do. I can see the shoulder underneath the clip. So there we are. We're finished. we're finished starting from scratch, making up a pinion for the minute wheel and mounting it into the wheel itself. Now, I don't know how much time we've been working on this. It's 20 minutes of 5 o'clock in the afternoon here on December the 14th, 1987. We started on this about 3 hours ago, about 3.5 hours ago, and in that period of time I've had quite a number of interruptions, but I suspect that the total working time on this has been about 2 hours. There's been some sizable little bit of it that have been off the camera, and there's been some things on the camera that really slowed down the operation too. But that gives you an idea of the problems that's involved, how they're solved, and how that a pinion for a dial train would be made. Now, one of the things that I did not show you, and this is one of the things that I usually do, in making that pinion, had I elected, I could have cut a stick of pinion this long. That means that over a period of time I could have sliced off pinion, 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 pinion. See, in just a very, very few minutes more, I could have made several times as many as I have here. When I was daily engaged in the trade and there was some probability of using those things downstream somewhere, that's the way I always did. I've got dozens and dozens of pinion remnants around here, and in all probability, if I had looked through my resources, I could have found a pinion that I could have fit to this. The point was, this tape is to